the metropolis, the first sentence, you know, it says essentially we can solve all problems of the materials. But the second sentence starts with classical statistics is assumed. And that's what we want to solve today. We want to move that to the point where we can do quantum problems. And that's a very easy step. So what is the problem? Why does metropolis only work for classical systems? And that was because we sampled the quantity A, which was the sum of a configuration C, some AC times PC normalized the sum over C PC. For that expectation value, we could use metropolis. When we have the quantum system, then it's not like this, but this A is the trace of A times exponential of minus beta H, for example, divided by the trace of exponential of minus beta H. Now, how do we calculate the exponential of a matrix? In general, we have to find all the eigenvectors and the eigenvalues, so we have to solve the full problem before this becomes a sum. So we need a way to convert this expression here into a sum like this. Once we've done that, then we can just use metropolis. The metropolis paper was written in the year 1953. There was another paper written in 1953 by Feynman, which solved just that problem, and that was the paper on the lambda transition in helium, where he introduced the concept of word lines, where he showed that one can map a quantum system to a classical system by looking not only at the particles in space, but the word lines of the particles in space and time. And those word lines then form as a classical statistical system in one more dimension. And then we can just use metropolis and update the word lines. And that's all that is to quantum Monte Carlo. We do Monte Carlo on word lines or diagrams. So with that, it could actually stop, because now you know all. But we have some problems with word lines and updates there. The first is, again, there will be some critical slowing down. The next problem will be local updates are fine for point particles. Local updates are not fine for line-like objects. If you have a word line like here, that's a nice word line of some electrons in this wire here, and there's a knot in here. And with local updates, I can do whatever I want. I cannot change the topology of the word line. I can't change knots in word lines, winding numbers around the system. I can do whatever I want with local updates. Nothing will change this. So local updates will have a problem. They will simply not be ergodic, unless we find a special move that removes a knot. But then we have to do any type of knot and winding numbers. And that can be very hard and very slow. So local updates works, but there's a very simple idea. How does one remove a knot from here? The simple thing is you take the word and you cut it. Once you've cut it in two, you can do local updates on the ends and remove the knot. And then the two ends move around with local updates. They meet again at some point, and we can close it and go back. So this is the so-called warm algorithm. It was a big breakthrough, and that way things work well also for quantum systems. So in the end, it all boils down to cluster updates or local updates of cut word line segments. You've learned about cluster updates, you know local updates. I told you the trick with cutting word lines, so now you know all the basics. But we have the whole morning now telling you a bit more details about that. So let me start with, and this I want to do most of the blackboard. First thing is, how can we go from an expression like this to a classical expression like that? One thing that will be taught the second lecture is called the stochastic series expansions. invented by hands from a refined by something. What we do there is we simply Taylor expand this expression. We take, for example, the trace of exponential of minus beta h, and we write it as a trace of the sum over n of minus beta h to the power of n times 1 over n factorial. This is now not yet a sum like this. So what we do now is we can rewrite the trace just as the sum of a complete set of basis states. So I rewrite the sum over some states I1, sum over n minus beta h to the power of n times the 1 over the n, the 12 here and over here, times I1. But still not a sum like this, because I still have to multiply the vector by this huge matrix. So what I do now is I insert a new set of states between each of these h's. And I write that as a sum over the n. And I write a beta to the n over n factorial. Then I write the sum over some states I1 to In. And now I write I1 minus h, I2 minus h, I3, and so on, till I have In minus h, I1. Why did that help me? Now I can just write down my basis states, the first one. That might have a particle sitting here and a particle sitting there, in some particle model. Then I write down the next state, I2, my state I3, and so on up to my state In. And then again there's the state I1. And this particle might now hop from this location to that, and then it might run straight, and then it might hop back. This particle here might just hop up straight. Now I just do a sum over all the possible configuration of the particles on these n levels. I sample them, and the weight of the configuration will simply be given by those matrix elements. And that way I'm back to something like this, namely a sum of the configurations of some weight. We have to be careful, though, that most configurations that you might write down randomly will have a weight of 0. Because if there's a third particle here, or that particle moves 2 steps, that might be 0. So we might start from just straight world lines of particles, and then we move around those world lines. I do not discuss yet how we do the updates. So that is one way of doing things. One thing that we have to be careful about that is we want to have all those weights to be positive. When they become negative, that's called the side problem, and that's what I'll talk about the next week. For this week, we want to assume that it's positive, and what Shemetko will tell you some tricks of making sure that most matrix elements will be positive. Now there's the second way of doing that. That is, we can just do perturbation theory and get the path integral. We can just write the trace of exponential of here minus beta h. I can split the h into some part h naught, which I can diagonalize and get easily, plus some perturbation b. Then I can write the trace of exponential of minus beta h just using time perturbation theory as a trace of the the time order the product of exponential of minus beta h0 times exponential of minus integral from 0 to beta v of tau d tau. And that one can expand in the Taylor series, and then one gets this extended diagrammatic expansions. So you can do any diagrammatic expansion that you've ever learned about, any word line like picture, and it can be turned into a Monte Carlo process. But anything you learn and you theoretically can be expanded and pushed further by Monte Carlo, as long as we don't encounter this infamous sign problem. So this would be written out as this series. We have the trace of exponential of minus beta h0 plus there's a term, this is the trace of exponential of, again now, of exponential of minus beta h0. So I have the integral over e tau 1, I have one term. I have exponential of minus beta, so minus tau h0. I have a v term, and I have exponential of minus beta minus tau times h0 plus the next terms, the second order, third order, fourth order, fifth order, and so on. And at that point, many people tell me that there's a problem with that because such series don't converge. Now let's have a vote again. Who thinks there are problems? Who thinks that this is not convergent?
That's the two different statements, problems and not convergent.
Who thinks that there are formal problems with that series?
Formal problems, it's...
Yeah?
I'm just waiting for someone to raise hands.
There are somebody who raised his hand, yes.
So for some type of tree at least, it's going to be an asymptotic series instead of a...
It's always an asymptotic series.
It's an asymptotic series for connected diagrams.
But it's a denominator, so supposedly you will have connected ones.
We work in a finite system at finite temperatures. In a finite system at finite temperatures, this is just an exponential function. The Taylor series of that is always convergent. The big advantage here is that as long as we are restricted to finite systems, we look at a finite system of 1,000,000 particles at a low temperature of 100 of Tc, the series is convergent. We get problems if we do a series like this and then manipulate it and say we now look only at connected diagrams. When we look at connected diagrams only for an infinite system, then the series might become asymptotic and then we can run into problems. So for those series you have to be careful. As long as you just look at the finite system of 1,000,000 particles at a low temperature of a millikelvin, there's no problem going with that series. You might have to sample to high order, but the contributions from some order on will decay exponentially. Because this is nothing but an exponential that we Taylor expand. So that's the big advantage of doing a finite system. Of course, if we have a system of the size 1,000,000 and the temperature of about the 1,000th of the coupling, then we might need to go to the 1,000,000,000th order, but it will converge. And the sampling will automatically sample the right orders. So we need updates that change the order and that change the configurations.
Sorry.
Yes?
But I mean, isn't this almost a trivial statement? The fact that you have a finite system just tells you that the second term will always be dominated by the first term. I mean, because of combinatorics, no?
No, there's a big term in there, the volume. And all possible, right? There's the volume factor in there. There's the beta factor here from the integral and the volume factor.
Yeah.
So we have a term in nth order like beta volume to the power of n, but it will always be divided by n factorial. And in a finite system, this n factorial will always win at some order n. When n becomes bigger than beta times volume, then that factor will win. For any finite volume, yes?
Yeah.
It's a trivial statement,
Yeah.
but the more senior the people are, the more they believe that such theories never converge. You want to get that out of your mind right now.
No, but the fact that you took the result for a finite system
Yes.
doesn't mean that you learned anything. I mean, you might be completely wrong starting a finite system. I mean, you made another statement. I think.
We sample a finite system, yes. Can you tell me any experiment that doesn't measure on a finite system?
Well,
So yes, we have to be careful.
finite doesn't have
When-
to be five sides.
When we are away from a phase transition, deep in some ordered phase, then the finite system doesn't matter because the correlation length is fine.
Okay.
When it's disordered, it doesn't matter because it's finite. At a critical point, you have to be careful because at a critical point, the relevant length case diverge. So there we have to learn how do we extract the right physics at a critical point, and that's what Roger Melker will also teach you, I think, on Friday. There's you have the finite size scaling and tricks that can be used to extract the critical behavior from finite size systems. But yes, you have to be careful to choose your system always big enough. But the advantage that we can only do finite system in the computer is that recently we started doing the connected series for the infinite systems, and then there are problems with convergence and so on. So it's much easier to study the finite systems.
Isn't V the perturbation?
V is the perturbation, yes.
It's not the volume.
V is the perturbation,
Okay.
but the perturbation, yes. So let's call it H1. But this term H1 is typically a sum over some bonds or whatever. It's the sum over some sides or IHJ of some term, of VIJ. So it typically scales with the volume. Yes,
Extensive.
it's extensive.
I'm sorry. I mean, if you have a topological liquid, also this series will fail.
Why?
If you are deep in the phase, in the topological liquid, let's say this is described by Simon's theory, then this thing is not going to converge, no matter what finite system size you have.
What will fail? In a finite system, if in a finite system, in a finite Hilbert space, finite dimension.
I'm sorry. I'm sorry. It will converge, but the finite system size will never give you the degeneracy of sectors. This is what I'm saying.
Make the gap exponentially smaller than the system size.
Yeah. You can find it. Yeah. You just have to learn how to deal with
Yeah.
the finite gap, the size effects, but you have to do the physics anyway, because they don't know any system that's infinite. So it's good that you learned that now and here. So, how was all of this done in the past? Before the Russians told us what is the nicest way, there was the famous Japanese Suzuki taught the decomposition, checkerboard decisions and so on. I tell you, don't worry about that. We will not look into this. Yes? There's a question.
You mentioned that there's some problem with the connected.
Yes.
Why is that identified?
When you look at connected diagrams, then you have a series for an infinite system. In those series, typically the factorial factor doesn't appear. And then it becomes the asymptotic series. But already in second order, third order, or fourth, you can already see lots of the physics, so you have to go to lower orders only, but it might not converge. So we will not do this here, we will go to something much simpler, because at the end, we will take finite time steps, and we will let the time step go to 0. So we don't care about the efficient method of doing things. What we do now for the next half hour is I will look at such path integrals, and I will for now just write them so this is going to need, this we don't need. I will not so the tail expanded, but what I will do is I will write this trace for exponential of minus beta h. I will write that just as the trace. And now the exponential of minus beta h, I split my time beta into small time steps. Time here goes from 0 to beta, I split it into small time steps delta tau. And beta is m times delta tau. So I write this as trace of exponential of minus delta tau h to the power m. So far it's still exact. And now I do the simplest expansion. The lowest order expansion, right? This is trace of 1 minus delta tau h to the power m. There are much smarter methods. What does Suzuki in second order, fourth order, and so on. I don't care about them. They just make it more complicated. Because for a lattice model, you can take the limit delta tau down to 0. For the continuum model, we can't do that. So there one has to be smarter. For the lattice models, we can just take the simplest approximation here. And now I do the same as in SSE. I just write this now as the sum over all possible states I1 to IM of I1, 1 minus delta tau h, I2, 1 minus delta tau h, I3, and so on, up to IM, 1 minus delta tau h, I1. And here the same picture as before. I have my states, my time slices, let's say I1, I2, and so on to after I1 again. And I have my particles or spins that move around. And the matrix now is just that of 1 minus delta tau times h. So let's look at some examples.
How does the error usually, for as a function of delta t, how does the error in your observable?
In this case, the error goes linear delta tau. There are better schemes where it's quadratic or higher. But here I don't care about it. I just want something that's linear, because in about 5 minutes we'll let delta tau go to 0. If you have a continuum model or continuous fields, then we can't do that. Here is the lattice that regularizes our the series. Without the lattice, it is not. So we take our system here, we have the particles, the world lines, because if we have a model that conserves particle number, then only those states will contribute which have the same number of particles on each time slice. Now let's look at one example of this. Let's look at a model of the particles, fermions or bosons, I don't care, which has a hopping term, minus t, and the nearest neighbor regards hopping term, and the nearest neighbor repulsion term v. Now I want to go through a few simple examples with you. The first is a straight world line, a single particle running straight. And I want to practice calculating the weight of these configurations. So here is just 1. Because when this particle runs straight, the matrix element of h here is there's none. So I just get that of the 1 here. What would be the matrix element of this configuration? What's the weight of this configuration?
Delta t.
0. 0, because the first state is not the last, it's 0. The trace doesn't close. So let's go to second order. We have a particle running straight, then it jumps back. The jump gives me a t, so it is 1 minus the tau h, that gives me a minus the delta tau t, so it gives me a delta tau t squared. Now let us have two particles run parallel. In this case, I get here the v term coming. So I get 1 minus delta tau v cubed. You can easily calculate the matrix element at each time slice. It's trivial. Here you have the particles, so it jumps away, it runs straight, it goes back here. Here we have a delta tau t, here we have a 1, and here again a delta tau t. It's very, very simple. The Monte Carlo updates are just as simple local updates. To put it to use a straight word line and make a kink. Metropolis, I have to calculate the ratio of the old to the new weight. This weight was, okay, or I can shift the kink in time. Those are two updates that I can do. The weight here was 1, the weight here was the delta tau squared. The weight here is in both cases delta tau t. Because this doesn't close, so I substitute human here. Yeah, that's the small part of the big worldline picture. And those are the local changes I do. So here, the acceptance rate to move that way is the minimum of 1 and the tau t squared. The worst way is the minimum of 1 and 1 divided by the ratio. And here, because the weights are the same, the acceptance rate will be 1. It's very simple. It's not more complicated in principle than the Ising model. But as we said, we cannot make knots. We can't change the winding of the word lines. So local updates will simply not be ergodic. And that's why we then want to move to some global updates, warm, directed loops, or cluster updates. But before we go there, I have to tell you that for about 20 years people simulated quantum spin systems, fermions, bosons, and lattices using smarter decompositions, here with like a small like error, but always in discrete time. And it took until 1996 that was changed. There was one paper by Beard and Wiese at the MIT. They showed how the cluster updates can be done in continuous time, and at the same time, the Russian group, Prokofiev, looked at a student coding such a method, and they asked him, "Are you stupid? Why do you do discrete time?" Now let me tell you something. We learned on the first day about how we do an integral analytically. We learned how to do it in an explicit way numerically. When we had the integral of a function, we took an interval and divided it into small slices, and then we placed this by rectangles, and we summed over those rectangles. Right? Now, imagine I tell you, now we do Monte Carlo. What we do in Monte Carlo sampling is we first divide the interval into rectangles, then we sample the rectangles randomly. And you tell me, why do you do that? We could just sample the whole linear space. We don't have to first divide it into intervals. Then sample, we can just sample directly. The integral can be sampled without discretizing it. So let us forget about these ideas of having to keep discrete time, and let us go directly to the limit of continuous time. So instead of keeping those time steps here finite, let me take the limit delta tau going to 0 immediately, before starting to write the program. Now, I did think about that already before, but But somebody told me, no, you shouldn't do that because you run into huge problems. The first problem you run into will be that you will need infinite memory. Because we have these m time slices, and if we let m go to infinity, we need infinite memory. Now that's not true, because as we make the time slices smaller and smaller, the weight for a particle jumping, which is linear delta tau, decreases. So that in the end, what we get as we take the limit of m going to infinity, the number of such jumps of the particles we have will converge to a finite number. And now instead of storing the configuration at each of infinitely many time steps, I simply store the times at which the particles jump. So I store the first step here, particle, hole, hole, particle, hole, 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 particle, hole. Then I say, okay, at time tau 1, the particle jumps from side 1 to side 2. At time tau 2, tau 3, tau 4, 5, 6, something happens. So I make a sparse representation of the configuration by storing the starting state and the times where things change. That way I need only finite memory. And the next problem are the weights of configuration and the updates. So what we get then formally is just the Bayesian series that I sketched down here. That's what we get in the limit. And let's look at what that gives us for the same model, for the same configurations. Have a particle running straight. When you're on straight, there's a terms of ordinary 0. It just gives me the exponential of minus beta h0, which in this case is 0, so the weight here is just 1. Now I have a single particle with a pair of kinks. That is a part of the second order term. The second order term there. If I write it down, let's write the second order term explicitly. Second order term will be just the trace of, now I have exponential of minus beta h0, so the time order of the integral from 0 to beta d tau 1 v of tau 1, and the integral 0 to beta d tau 2 v of tau 2. When I write that explicitly, then I get an exponential of minus tau 1 h0, a v exponential of minus tau 2 minus tau 1 h0, the v exponential of minus beta minus tau 2 h0, and I have the trace in front here and the double integral d tau 1 d tau 2, where tau 1 goes from 0 to beta and tau 2 from tau 1 to beta. So this here is now one certain configuration in this integral. I pick randomly one value of tau 1 and one value of tau 2. To sample the orders and to sample the integrals at the same time. And what does that give me here? The weight that I get here is just the value of the integrand here. And the h naught will just be 0. So it's easy here. I have a minus v, don't forget that. So I have a minus minus t squared, so I have a t squared, d tau 1, d tau 2. You have an infinitesimal weight. And infinitesimal weights, that's what we didn't really like. And so we never looked at that until those Russians told us, hey, you're stupid. Next case, two particles running straight. This case is very simple again. Order 0. There's an energy v here, so the weight here is exponential of minus beta v. Let's look at that configuration. We have the t squared, d tau 1, d tau 2. We have here and here a v term, so we have an exponential of minus tau 1 v and the exponential of minus beta minus tau 2 times v. The repulsion here. So the weights can again be easily calculated for any configuration that you write down. But you might believe there are problems with those infinitesimals. Because now let's look at the updates. We want to insert, so we want to shift the kink in time, and we want to insert a pair of such kinks in the word line. Those are the two simplest updates. This one is easy because the weight here and here is the same, so you can always accept it. Here's tricky. This has weight 1, and this has weight delta tau t squared, which goes to 0, which goes to this infinitesimal weight. So if you now calculate the acceptance rate for this naively, it's the minimum of 1 and delta tau t squared, and the limit delta tau going to 0, it vanishes. Boom, we're done, we can't do it.
Russians can.
The Russians can, yes. Because they said, okay, yes, because they said, don't be so confused, but think clearly about what we want to do. And I talked to you about Metropolis update on the first day. And I talked to you about the acceptance rates. There were two steps. There was the a priori rate to propose it, and there was the acceptance rate. So now let us work through that by hand and carefully and see what comes out. And then at the end you will realize that you get a final acceptance rate if you understand what detailed balance is about. Which the Russians did and we didn't. Okay, and then the Russians wrote a nice paper, completely unreadable, unless you know the solution. Because they told me, in Russia they learned that you shouldn't write anything in the paper that's written in any textbook anywhere. So the paper was unreadable, but I hope I can teach you the basic now. And if you want, you can then read the paper and then it should be readable. It was rejected from FB because it was unreadable. So, what was the basic idea? You want to have a straight word line. Let's say that some interval that goes from 0 to a time lambda. Now we want to insert this pair of kinks. A time tau 1 and time tau 2. What is the process with which you do it? We have a certain way of selecting the points. Right? So let us select 2 points randomly. The point tau 1, the point tau 2. What is the a priori rate? So let's say that is configuration x and that is y. What is the a priori rate of going from x to y? I choose a time tau 1 and I choose a time tau 2 randomly. What is the probability for choosing the time tau 1? It is d tau 1 divided by lambda. And that is the probability of choosing that. You have an infinitesimal probability of choosing a certain one. What is the probability of choosing the second one? D tau 2 over lambda. I always want to make sure that tau 2 is buff tau 1 here. So I want to divide this by 2. But be careful in what you do, because if tau 2 were below, I would exchange the 2. So what we get is that a priori rate is d tau 1, d tau 2 divided by lambda squared over 2. You see, it's very easy to make mistakes in factors of 2 here. And that's where detailed balance becomes tricky. You have to really know what you do. You see, I choose a tau 1 and tau 2, and if tau 2 is smaller than I swap them, that gives you the factor of 2. And it can take weeks to find such errors. Now, what about the reverse step? The reverse step is I pick these two kinks and remove them. Now, there's only one way of picking it. So lambda yx is just 1. So a yx is just 1. In the full code, it's a bit more complicated because you have a big set of the word lines and the kinks running around. And you now have to choose, okay, which set of kinks will I remove, and then it becomes a bit more complicated. I want to choose the simple example to show you the basic idea. So, and the weights were d tau times t squared. So now we have for the acceptance rate, for the probability to accept a move of going from x to y, because the minimum off. Now it was the a priori rate of going from, I have to remember which way dollars was. And the a priori rate of going from y to x divided by the a priori rate of going from x to y times py divided by px. And minimum that in 1. So that is the minimum of now the a priori rate of going from y to x is 1. And of going from x to y was beta 1, beta 2 divided by lambda squared. So there's a lambda squared over 2 here. And what was the probability ratio? In the one case it was t squared beta 1 beta 2. In the other case it was 1. And you see the infinitesimals drop out. We get here the minimum, this is the one, the minimum of 1, and now I get lambda squared t squared over 2. I get a finite acceptance rate. You can do the updates, but you have to be a bit more careful about what is actually the error rate with which you propose the updates. And then when you write it down carefully, then all these standard taus will cancel. There's no problem in the end.
What breaks in continuous space?
Huh?
What breaks in continuous space?
What breaks in continuous space is that your paths become ground in motion. And they need infinite memory. You have I'll take up the violet problem. Yeah.
Can't you say this turn to a position process instead of like a Brownian motion in some sense?
On the finite lattice,
Yeah.
it turns into a Poisson
Position,
process.
yes.
Yes, exactly. And that's discrete and so it works. So, you can do the updates easily and there's no problem. Of course, sitting down and exactly proposing an update here now, I might say, okay, to insert it, I go to a certain pair of sites. And then I have to find some interval in which I can insert something. Now I have to think about what is exactly the priori rate of picking that interval. So it's a bit more subtle actually than to do exactly equal to what the updates you do, but this is the idea. You have to think, okay, in my updates, I will choose a certain bond randomly. There's 1 over number of bonds. And on this bond, I will choose a certain time point, for example, randomly for tau1. So in that case, you get that AXY would be 1 over number of bonds. Then you might have a d tau1 over beta, which choose that. Then you look at the second one. The second one now can be inserted anywhere between here and here. So let me call this up here capital T, or T1. Then the second one has to be chosen in this interval. So for the second one, it will be a d tau 2 over capital T minus tau 1. So that will be the insertion rate here for the removal. Now it's not just one, but you have to pick the bond again, and you have to pick the segment again. So it looks a bit more complicated, but it's the same basic idea. You have to write down exactly the rate with which you choose a certain update. It's very easy to make mistakes there. In the Ising model, it was trivial. I picked a spin with 1 over n. It is deceptively simple there. In more complicated codes, this is not trivial. But when you think about it carefully, it's no problem to write down the equations. What are the advantages of continuous time? The main advantage is I don't have to extrapolate in the time step. If I do a simulation at the final time step in order to have an accurate result, I have to extrapolate. to run it at the various time steps and extrapolate, or I have to say I choose it small enough so that it doesn't matter, but then I prefer to extrapolate instead of believe things that is small enough. And I don't get additional errors from the extrapolation, and that makes it already faster. The next reason why it's faster is I need less memory and time, because instead of having a very fine mesh, if these are word lines, then I would need a mesh that is much finer than the typical distance between these chunks. So I need the tau that's about 1/10 of the hopping or so. I need to store the configuration at each of those slices. In continuous time, I just need to store the times when the jumps happen. So that's about a factor of 10 less things to store and less variables to update. And the updates are a bit more complicated, but in the end we found that the speed up of about a factor of 10. And the other advantage is that way we've now seen that actually we can sample any sum of integrals. We can sample any analytic perturbation expansion series. Diagrams, any type of diagrammatic series you have, can just be sampled. So, and that's what we will now do for quantum spins. Yes?
Are there some disadvantages? I mean, are there some...
The code is more complicated.
Right.
You have to now pick the times like this, to go like the rates were here, it was trivial. You picked like that was straight here. That was one word line running straight. We have color here somewhere. So we said that was one word line running straight. These were the time slices. And I said I want to change that straight word line to one with kinks. And pick one time slice randomly, 1 over m, and then make this kink here. It's as simple as in the Ising model. Here, the code becomes more complicated. But in the end, it's faster. It might take you longer to code it. The first time I wrote the continuous time code, it took me a month. The second time, it took me a day only. The first time I wrote the discrete time code, took me a day. So, but I didn't have people explaining to me all these nice other things. I had to read the Russian paper and understand it and find the bugs myself. So yes, it takes more time to code. But here it's about a factor of 10 faster. For fermions, the scaling goes typically with a cube of them time slices, then you gain a factor of 1,000. And the factor of 1,000, or with the new method we got out, the factor of 100,000, means you can do on your laptop what would before need the supercomputer. So for fermions, that's a huge advantage. And that's what Werner will teach you in the last week of the school. But now we go to cluster updates. And we want to use the 71 cluster updates for quantum spins. What were the problems with local updates? Local updates could not easily change the number of the particles of the organization. It can't change the winding of word lines around regularities. It can't change breaks or knots in the word line, so it's just not ergodic. And the scaling is slowing down. And that can be solved by the cluster updates, and then the first interface transitions you heard from Simon, the tapes guest today, how that can be solved by extended ensembles The same techniques can also be used for quantum systems. But if you've mapped it to a classical system, then you can use the same ideas. So now, I want to revisit the cluster updates. So let me first ask, is there anybody here who had problems understanding the cluster updates? Then ask now, because it will only get more complicated now. So the cluster updates were, we looked at the spins, we looked at neighboring spins. If two were parallel, then we asked whether we want to connect them or not, and if we connected them, then we flipped them together. So now I want to make this whole thing formal. And always keep in mind the Ising model if it gets too abstract. And could someone bring the blackboard, please? So let me sketch a simple 4x4 Ising model. Let's make some 4x4 spins. So what you can do here is you can think about the cluster updates as looking at all the bonds in this lattice. And you look now, and if two neighboring spins are parallel, then I might or might not flip them together. When I want to flip them together, I put a bond in here, a graph them, saying these two spins are glued together. Let's say when they are not parallel, then they can always be flipped. So that's fine here. But let's say maybe I want to glue this to this, but not this to that. So for all those pairs of spins which are parallel, I draw a random number and then decide whether I want to connect them or not. And that way I find, for example, that those get connected and the others not. And now, once I've done that for all the bonds, then I can find the cluster of connected spins. And those spins will have to be flipped together. What we've done in the first lecture is we picked a single spin and we drew a cluster from that one. So I can say, okay, I jump here, I look at the neighbors, and I check which spin should be flipped with it. I can either build all the clusters and then flip half of them randomly, or I can just start from a single spin, build one cluster and flip that. That doesn't matter. Now I want to write this down in a formal way, and I want to prove detailed balance, because there was the question whether that really satisfies detailed balance. And that goes back to the framework by the Candland. The money. So what I do here is I write my partition function Z, which is formally the sum of the configurations of the weight of the configuration. And now I extend my configuration space. And I not only have configurations, but I have configuration C, and I have a graph G. The graph G are just those the connections of the cluster. So my phase space now has configurations and graphs. I want to write the weight of my configuration as a sum over all graphs of the weight of the configuration in a certain graph. That way now I can write this here as the sum over the configuration and graphs of the weight of the configuration in the graph. Next, yep.
What do you mean by graph here?
I label my edges with either the connected or disconnected label. It's okay, these two spins might be connected. That's this edge here of the graph. If those two are not, then there's no edge here. So the graph are these red lines, the clusters I built. And for each set, and now look at all the configurations and all the possible red lines I can draw, or the graphs that I can draw on this lattice. These are all possible ways of either putting the two spins connected or not. So, and I look at this certain configuration, I look at all possible graphs that I can put on there. I want to find a smart way of designing a way to each possible way of putting the red lines down here. That can be done, and if any way I choose here, as long as this is here satisfied, I get the same partition function. But it doesn't help us much yet. So we want to have a certain way of doing it. And for that, I choose the following way. The weight of a configuration in the graph should not depend on the configuration except in a very certain way. So I want to write that as a delta function of the configuration in the graph times the weight v, which is only a function of the graph. So I want that to factorize in one function delta that tells me whether a certain graph is allowed for the configuration, and then a weight that does not depend on the configuration but only on the graph. So this one step I do, and the other step is I can factorize the whole problem. Because the weight of the configuration is just exponential of minus beta times the sum of all the bonds I and j of the energy E ij. Or here of your, here it was minus j times sigma I sigma j, the Ising model. Let's factorize it. That's just the product of all bonds I and j of exponential of beta j sigma I sigma j. So the weight of the configuration factorizes into the product of all bonds I and j of exponential of a weight w of the bond of the configuration Cij on that bond. And to do the same for the graph weights. Also want the delta of C and G to factorize in product of I and j of a delta of Cij and Gij, and the V of G should also factorize into a product of I and j of V of the graph Gij. So I only need to look at a single bond now.
Is it easy to see that this doesn't overcount the total number of configurations?
That's the equation we need to satisfy. It doesn't overcount. But we have to satisfy that equation. Right? I didn't put down the solution yet, I just made an ansatz. Now we need to see whether there's the solution to that ansatz. So what would we do here? Let's make a table over there. And this is now really overkill for the Ising model, but it will help us do the quantum models there. So for two spins, they can be up, or they can be down, or they can be up, down, or they can be down, up. And let me write down here what were the possible local graphs. You could either have two sides disconnected or two sides connected. Here I want to write down this delta function. And what were the rules? The rules were when two spins were parallel, they could be connected or not. If two spins were anti-parallel, they were never connected. So actually here, in this table, this gets a 0 and this is all 1. two spins can be connected if they are parallel. So that is essentially this delta function. It tells me when can I connect two spins. For the Ising model was they could be connected if they were parallel. But now I need to find the solution here where the weight of the configuration in the graph can be written in that way. As the delta function times the weight of the graph. Let's do that right now, and afterwards I tell you why that helps us and why that is enough to prove detailed balance for the updates. So here, let us write down the weight of the configuration. The weight of two upspins was exponential of beta j. Two downspins was exponential of beta j. Up and down was exponential of minus beta j. Down and up is exponential of minus beta j. Now I want that weight here. That should be always the sum over all graphs of the delta function. The weight of the configuration should be the sum over all graphs. Delta function of the configuration of the graph times the weight of the graph, v of g. Let me here write down v of g. It's easiest to start from this case. This connected because there's only one possible local graph segment. It has to be disconnected. So this here I have to give a weight exponential of minus beta j. That way I satisfy the equation. For two spins that are not parallel, there's only one graph allowed, and its weight is exponential of minus beta j, which is the weight of the configuration. For two spins that are parallel, I have both possible. So I need to assign to this exponential of beta j minus exponential of minus beta j. Now when the two add up, I get the weight. So I now found an assignment for this graph weight v of g and for this delta function that satisfies this equation here. Whenever you can find that, you can design a cluster update algorithm. There is no double counting because we now have found the explicit solution. If you don't find a solution, then you can't use that scheme. But now let me prove detailed balance. And for this, a bit of space down here. What do the updates do? The updates start from a configuration C. And from here I go to the configuration C and the graph G. So I put a graph assignment onto my lattice. What does that mean? That for each bond I pick one of the allowed local graph segments. That is connected or connected. And I pick that proportional to the weight v of g. It's just direct sample. For each bond, I pick one of the graph segments with the correct weight. So then here, I satisfy detailed balance. So I pick it with the correct weight. Next, what I do is I pick a new configuration, C prime, but keep the graph. What does it mean? I might just flip clusters of spins. I might flip spins. I might flip this spin or that one. But keeping the graph means that if I flip the spin, I have to flip them in such a way that the same graph is still allowed. I can't flip just this spin here, because then two spins that are not parallel would be connected by a graph segment. So the only new configuration I can get is one where I flip whole clusters. When I flip the whole cluster, then all upspins here in the cluster become downspins. And for all downspins, I can still have them connected. So pick a new configuration that has a non-zero weight. Let's get theta balance for this. what is the ratio of the weights? The weight here was the W of C and G, that was the delta function of C and G times V of G. The weight here, prime and G, is the delta function of C prime and G times V of G. What is the ratio? If we look at the ratio, W of C prime and G divided by W of C and G, that enters the detailed balance equation, then you see that it's just delta function of C and G times V of G, C prime times divided by the delta function of C and G divided by V of G. The delta functions, if one of them is 0, then I wouldn't even pick the configuration. And it starts from a configuration, I assign a graph that is possible. So the V of C and G, so that delta function here is known to be exactly 1. The V's of G drop out. So that ratio here just becomes delta of C prime and G. So the acceptance rate will be 0 if the new configuration is not allowed by the graph, meaning if I flip the spin in a cluster, the ratio will be exactly 1 if the new configuration is still allowed. So all configurations that I can reach from here by flipping clusters will have the same weight.
How do you choose the C prime? Is it like locally related to C?
So now I can choose any C prime that allows the same graph. So, and what that means here is the same graph is allowed as long as I flip all spins in a cluster. So I could just pick a single spin and flip that cluster. Or for each spin I could decide with the probability of 1/2 to flip it or not. So the cluster or not. Or for each cluster I could choose with the probability of 0.1 that I flip it or not. Or for each cluster I could choose with the probability of 1 that I flip it, but that's not really useful because then I flip all spins always. You can use any of those schemes. What enters there now is the a priori rate of picking the new C prime. You could say I pick a random spin and I flip the cluster. And the a priori rate becomes 1 over n. And it's all nice and fancy. I could say that for each cluster I choose with a probability of 1/2. Both schemes are fine. What I showed you in the first lecture was picking one spin and building the cluster. From there, this is like picking the one spin and flipping that cluster. Now this is the formal proof. It works for the Ising model. It also works for the other model. This proof is overkill for the Ising model. But now what we'll do is we'll go to quantum spins. And for quantum spins it's a bit more complicated, but the same framework will hold. So, this is the calculation of the balance. That was the table we discussed. So yes, one more thing. What is the probability now, given two spins that are parallel, what is the probability of picking the graph that connects the two? It is the weight V of G divided by the total weight. So it's exponential of beta J, that should be minus here, minus exponential of minus beta J divided by the total weight, so it's 1 minus exponential of minus 2 beta J, which was just the rate we had for the Ising model. It's just the same algorithm. And then in the 23, Hans Everts realized that the same algorithm can be used for quantum spins. But it's a bit more complicated because for two spins in the Ising models, but I could just flip a single spin easily. And I could say for two spins, it could either be connected or it could be disconnected. But for quantum spins and world lines, it's not that easy. So let's look at some small time step, the d tau here. And then what we know is I can't flip a single spin. Because the time evolution Heisenberg Hamiltonian, for example, conserves the total magnetization. So I can't flip a single spin. But I can, for example, flip these two spins. So I can glue those two spins together. Then I might get such a configuration. In this case, I could, for example, glue those two spins together. And get to that one. In this case, I could glue them across. And that one, or I could take all and flip all spins. Not all cases are allowed always, but we always have to flip at least two spins together. So on this local plaquette of the time evolution, I either have to glue the spins together in a time-like way, in a space-like way, across, or all four. So those are the local graph segments I can use. I cannot take the fully disconnected one because that would break the conservation of the magnetization in the Heisenberg model. So let us look at just a local segment, two sides of a spin half model. We have term here, we have the Jxy, the term Jc, and the field term H. And now here I write the local matrix in the basis here for both spins up, it's just Jc quarter plus the field H. The spins down is Jc quarter minus the field H. And for the up down, we have the down up is the minus Jc quarter, and here's the Jxy half, and here again there's a minus Jc quarter. When the field is non-zero, you cannot use cluster updates. Cluster updates only work when the weight of spins pointing up and spins pointing down is the same. So the moment you apply a magnetic field, cluster updates can't be used anymore. So let us drop the field for now. Let us look at the XY-like antiferromagnet. Well, that might not be the best idea because, no, let me show that one because there's a subtlety here that I want to mention. Let's look at an infinitesimal part of my word line. What is the weights if there's one spin going up straight and one spin down, or one spin down and one spin up? The weight, if you remember from back here, was in I1, 1 minus hd tau I2. So here I have 1 minus h times d tau, that's the weight, and h was here minus jc over 4, so I get a weight here 1 plus jc over 4 times d tau. What is the weight for two spins which are parallel? It is smaller, it is 1 minus jc over 4 times d tau. What is the weight for the exchange term where they cross? It is minus jxy over 2 times d tau. Remember, it is 1 minus h d tau, and here there's a plus jxy over 2. So here we get a minus jxy over 2 times d tau. We have a negative weight. We have a sign problem. I will tell you next week how to work around the sign problem. What we do for now is we restrict ourselves to a bipartite system. On a bipartite system, we can make a gauge transformation that gauges away the sign. You can view it in the following way. When you have a system where the lattice is the bipartite, then there has to be an even number of jumps to go back to your starting state. On a square lattice, we need even number of the exchanges, so the sign here that does not matter. On a triangular lattice, on a triangle you can jump back in 3 steps, then you'll get a sign problem. We now look at only at bipartite lattices where there's no sign problem, then the sign can be ignored, and I choose here the weight jxy over 2 times d tau. And now I have to find an assignment of weights to these graphs. And first let's look at this delta function. There are 3 entries here that I mark with a dash. That means this graph is just never allowed because it would lead to breaking the observation of the magnetization. Like here in this case, if I glue those 2 pins and flip them, then I get to a state that goes from up to down, and that's not allowed in this model. So here there's a dash, meaning that's not allowed. The others are allowed. And now I need to find an assignment of 1s and 0s to the delta function, and an assignment to the graph weights here that then we have to satisfy my rule that the sum over the delta function times the here the graph gives me the total weight. And here's one solution I can find. There's always more than one solution. I look for one now where the freezing graph, the one where I flipped all spins, where that had weight 0. So that I flip as small clusters as possible. And then this is now one way of doing it. I have a weight of jxy over 2 times d tau of making the so I have for the exchange I get jxy minus jc half times d tau. For that here I take jc half times d tau, and that one here, the straight one, that's it's possible in all the straight word line configuration. That gets the smaller one here, the 1 minus jc over 4 times d tau. Now I have those weight assignments. Now I do the same as in the IC model. I go to my lattice, I assign these local graph segments. But what does that mean for the word lines in continuous time? Let's look at a state where I might have an upspin, like I'm here, and then I jumped across and then I went straight. There was an upspin word line that went straight, and in blue I draw a downspin word line. It has to exchange twice. Blue to a downspin word line, then exchanged like this. The one thing is simple. When I have such an exchange like here or here, then what is the probability to choose a certain weight? The graph weights, this was jc half times d tau, that was jxy minus jc half times d tau. If I divide it by the sum, then the probability for this graph becomes jc over jxy, and for that becomes jxy minus jc over jxy. So pick either that connection across, or this one randomly with those weights. That's the easy thing. For each of these jumps that you have, you pick one of those graphs. The trickier thing are the infinitesimals. When I had this case of 2 parallel word lines, which happens everywhere essentially, then the probability of choosing the straight one, here the graph weight was 1 minus jc 4 times d tau, and to go across in a space-like way, it was jc over 2 times d tau. If I normalize that, I get here a probability of 1 minus jc half times d tau, and here I get a probability of jc half times d tau for jumping. How do I deal with that? I get an infinitesimal way of inserting that graph anywhere. You already heard the word Poisson process. Essentially, this is a Poisson process. It's like radioactive decay. So the problem we had is here, I mean, this was essentially 1 in the limit, and that went to 0, so at first one didn't think it was possible to do the cluster updates. But then you just have to reinterpret this. You have to say, okay, when you start here and you go up, you have a local probability density of j half times d tau for having a graph that goes in a space-like way. And the way to get that is you simply take this Poisson process, you calculate a decay time, like in radioactive decay, and that time you insert such a graph. Then you draw your next random number, and that time you insert that graph. Those decay times are exponentially distributed rate of j half. In the first lecture we learned how to calculate exponentially the random numbers. So what we do is we go here, down here, we start here, and we calculate a decay time tau. Then we run up the time, here we insert such a graph. Then we draw the next time, jump up here, we insert this graph. Or the next random time, it might end up here, the next one might end up there, and we're done. Then we start here, we draw a time, and it might be here, but I cannot insert it between two spins that are then in the case of the anti-ferromagnet magnet that we saw on this table here for the anti-ferromagnet probability of having. So this graph here I cannot have between two spins that are parallel. So, but I might have it up here. And all the rest runs time-like. Once I've done this, then I have a picture like this. I start from my word lines. I draw write just the upspin word lines. At the jumps of the upspins, I insert either the cross graph or the space-like one. Then I look at each bond and insert the decay processes where it's possible. Then I start somewhere and I build a cluster. I might start, for example, here. I run up in time until I reach this vertex here, and here I jump over space-like, then I run down. So space-like go up, and space-like go down, space-like go up, space-like go down, and so on. I come out here, and go here and here. Until I close my cluster, and then I flip all spins on this cluster. Or I might start here. If I start here, then I go across, so I go down here, and I run here, go up here, and so on. These clusters will always be loop-like, and that's why it's called the loop cluster method. When you flip all spins on a closed loop, you always conserve automatically the totality of the magnetization. So that way we can do cluster updates for quantum spins. It's quite a bit more complicated to code than the cluster the updates for the Ising model. So what you want you to do is the homework once you code it in Python or C++, the local updates for the Ising model, we want you also to code cluster updates for the classical Ising model only. The loop algorithm might take a bit longer to code. But it's the same basic idea, it's just a bit more complicated because of this continuous time aspect here. That's where I want to stop. If you want to use the loop algorithm, there is no need to code it, because in Alps we have a very efficient loop code that you can use. Any questions? Yeah.
So this discussion in the beginning about series and fields, them being asymptotic or not, does it mean that these methods are very good for doing partition functions and thermodynamics, but they're not so good for Green's function and correlation functions or things like that?
That's the very good question. Green's functions, okay, when you look at correlation functions that are the diagonal in the basis you choose, like the CSC correlation functions, it can just be measured directly in that configuration, in the basis. There's no problem. Green's function is a bit trickier, because the Green's function means you want to measure something where you have some S plus here and some S minus there. There's some word line here. So that's the configuration that does not conserve the word lines. To measure that, you have to actually go into a new configuration space that allows you to have one broken word line. It's just what I said, that when you use the warm algorithm, when you cut this up, then you essentially sample the Green functions. When you close it again, you sample the partition function. In the loop algorithm, you can measure the 2-point Green function directly by flipping only half a cluster. You can pick 2 points and flip half a cluster. So you can measure it directly. Measuring 4-point functions, you need to have 4 open ends. It can also be done.
So just at the level of feelings, is it the same as breaking, if I do diagrams for thermodynamic potential, they're all loops, right? Is it the same as breaking loops or not?
It's the same as breaking loop, yeah.
Okay.
Yes. Yes. So the problem comes when you go to a series for an infinite system. Then if you do the direct expansion, you need an infinite number of terms. When you go to the connected diagrams, you can get the series where you get results from a finite number of terms. So the series becomes asymptotic. As long as you restrict yourselves to a finite system at finite temperature, there's no problem with convergence. Unless the Monte Carlo updates get stuck somewhere, or it's not ergodic, or it's inefficient, it's slowing down. But in principle, the series has no problems. We have problems reaching the ground states in big systems. Reaching the ground state means you have to the temperature and lower it until you see things converge, and then you can extrapolate to the ground state. Same with the system size, you have to increase it until it converges, and then you're done. Yeah.
I'm a little confused by the fact that when you use metropolis, you use it to calculate probabilities. You cannot calculate partition functions.
We cannot calculate, correct, we cannot calculate partition functions.
So this means that
We can calculate averages.
no matter what you do, you essentially calculate connect diagrams. And probabilities are connect diagrams.
Yeah, we also sample disconnected diagrams.
No, I understand that you sample disconnect diagrams, but
These are, these straight word lines, these are disconnected diagrams.
I'm sorry, but at the end of the story, you sample probabilities. So the probabilities are numerator over the denominator.
Yes,
And
correct.
the denominator, when you bring in the numerator, you cancel all the disconnect diagrams.
No, we sample the disconnect diagram. We don't cancel it. That's the trick. In the finite system, we sample all diagrams. When you do it analytically, you cancel out all the disconnected diagrams. And that gives you convergence problems.
Yeah, but I'm saying again, I mean, of course you can have in your mind that you sample disconnect diagrams, but at the end of the story you do metropolis. Metropolis has probabilities, no?
Yes, but I do the probabilities of disconnected diagrams. These three straight word lines, these are three disconnected, this is a disconnected diagram. Okay, so here's 0 to beta closest in time. These are three loops disconnected. I don't cancel it. I sample also those. Once I restrict myself to connected diagrams only,
Wait. But they cancel on their own, you know?
No.
They cancel.
no, they don't cancel on that. I write a sum of all the configurations. So for the AC, then the measure times the weight PC, divided by sum over C, PC. And here the C's contain also disconnected diagrams. What you can do, you can be analytically smart and say you can rewrite that in terms of connected diagrams, and you cancel out the others. Once you do that, you run into convergence problems. I sample all diagrams. When you go to disconnected diagrams, you analytically transform this sum in a smart way, which helps you with the pen and paper, but which gives you convergence problems. It's powerful, but it will not converge in all cases. We don't do the trick here. We just sample also the disconnected one, because remember, in sampling, the error is just the square root of the variance of the quantity I want to sample divided by the number of steps I do. It does not matter how big the space that the sample is. I can sample connected and disconnected, doesn't matter, the error doesn't increase. The effort in sampling does not increase when you increase the dimension. That's the nice thing about Monte Carlo. So I don't care that I sample many more things than I would have to sample. I could be smart and say I sample only connected ones, then I run into problems. Yes?
Can you ask a more basic question? When you first introduced the loop algorithm,
Yes.
you gave us a set of rules, like these little croquettes with spins.
Yes.
2 spins or 4 spins being flipped.
Yes, that was examples of spins being flipped.
Okay, so
Yeah.
is that based on like this Hamiltonian that you gave us?
That's based on this Hamiltonian, which,
The XSE model that you
yes, correct. When you don't have U1 symmetry, then you get more graphs that are possible.
So what are the diagonal effects? Because it's flipping, it's connecting a spin with space.
So this here means that you have to flip the 2 spins that are space-time neighbors together. Let's go back to this picture. I mean, this picture here.
Yeah.
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 So these blue ellipses here become the things which I can connect here. When I take this here and I put on this graph label, that means I have to flip those 2 spins together and those 2 spins together. One example is this up here, I flip those 2 spins. Once I flip them, I end up in that configuration. In this case here now, I've assigned that graph, for example, at a later time. That means I have to flip always 2 space-like neighbors. So they are on the same cluster. So I have to flip those 2 spins together. If this gets flipped, also that gets flipped. Just like in the Ising model, when 2 spins were connected, they had to be flipped together.
Is it possible to think about this as a classical model in +1 dimension?
It's a classical model in 1 higher dimension.
And that will be the same as before?
Yes. In discrete time, it's just that. There are these the time slices in discrete time, and that tells you will have to flip those 2 spins together. For the classical Ising model, we could have a single spin flipped individually. Here, we can't have that because we always have to connect 2 of the 4 spins. This graph here means when I flip this spin, I have to also flip that spin. This graph here means I have to flip all spins together. Yes?
Alright, can you explain again why some of these graphs aren't allowed?
So you take this configuration here, all up spins, and assign this graph. This means that if you flip this spin, also that spin has to be flipped. Let's do that. Then we end up with a configuration that has 2 down spins here, 2 up spins there.
Well, then you can put them back again.
if I have two downspins here and two upspins there, and I have a U1 symmetric spin model, and the matrix element of H between those two states is 0.
Well, that's true for any just single bond operator. Right? Isn't it? If you just flip, if you flip any of the spins, then you have to flip them back somewhere later in the Rorban.
Globally, yes, but locally here, this here has the matrix element of jxy over 2 times d tau. This here has a matrix element of jc over 4.
Okay. So you're just applying all
But-
three of these.
But if I have down, down to up, up, it has a matrix element of 0 in a U1 symmetric spin model.
Okay, so you're just applying all three of these bonds at once. All three of these spin flips.
So is it the consequence of the fact that you have S plus times S minus only? Or?
It's just the fact that if I have S plus times S minus, if the model is U1 symmetric, then these matrix elements here from up to down is here, and that is 0. Up to down has a 0 here, and that's why I don't even have to look at that. So I cannot do an update that leads to here. If the model is not U1 symmetric, if I have a JX, JC that are different, then this all will be the non-zero, and then that will also be allowed. There will be more graphs allowed there.
Coming back to the same issue, I have the impression that if you have periodic boundary conditions in your cluster, you cannot allow disconnect diagrams because the system is already infinite. I mean,
No.
You're playing a trick by the fact
No.
that you have a boundary.
When I have periodic boundary conditions, I still only have a finite number of degrees of freedom.
But you do have an infinite system. I mean, these
No.
are periodic boundary conditions.
No, it's finite. It's a finite system with periodic boundary conditions.
You can enumerate them with the finite.
It has no boundary. It's a boundary-free system, but it's finite.
Okay, if you take,
Here, there are 3 particles.
I'm sorry. If you take your little box and
Yeah.
produce all the identical parts,
It's a finite number of degrees of freedom.
A little bit less than
A little box is finite.
okay, but
It's a little box, but when I walk out this door, then I walk in there and I'm still in the same room. We only have a finite number of students, even if the boundaries were periodic. You're the same person no matter whether I walk out there and back in again.
no, what I don't understand is when you finally calculate the expectation value,
Yes?
why the disconnect diagrams do not go away in a system with periodic boundary conditions?
Because the sample also the disconnect diagram. The sample is
You
here.
can do something, but they should go away.
No, they don't. That going away is an analytical trick you do. You can rewrite this sum
No, it's just
into a new sum.
you do numerator and denominator separately, right? When you divide one by the other, you'll get the previous result that you would get on the paper, as you say, by canceling those diagrams.
You don't say it, huh?
But you can say, okay, I do not cancel. I just grab that numerator and do this,
I'm saying,
right?
but